From before lunch, we found our... So anyhow, we're going to start now, right? Oh, good. Before lunch, we got our derivative of that thing. 4x over the cube root, 4x over 3 times the cube root of x squared minus 4. What do we get from the top for a critical value?
0.
0.
Also,
what do we get from the bottom for critical values?
-2 and 2. Also, what was an example of Miss Ebern's?
Not right now. Okay. Not right now. We don't have time right now. Okay, we're going to make our number line. I think it's kind of up to you if you want to plug into this version or plug into this version. By the way, are you allowed to take cube roots of negative numbers? Sure you can. Square roots, no. But cube roots, really any sort of odd root, yes. Do you want to do the plugging in together, or do you think you can do the plugging in? See if you can do your plugging in. Remember, we're plugging into the derivative. You've got your 1, 2, 3, 4 regions. Go do it. Go plug in. So I'm going to plug in 3. Maybe I will use this version. 3 squared minus 4 is something positive. Cube root's positive times 3 is positive. Top is positive. It's 1. Or no, it's not 1. It's positive there. Plug in, I think 1 would be a good number to use. 4 times 1 is positive. The bottom, 3 times... What happens with the bottom if you plug in 1? I think negative, because 1 minus 4, negative 3, cube root of that is some negative number, positive on the top and negative on the bottom. That's going to be negative. I think negative 1 would make sense to plug in. 4 times negative 1 is negative 4, well, something negative on the top. Negative 1 on the bottom will make the bottom what? Positive or negative?
Negative, like the last one.
Negative, exact same logic as the last one. So negative over negative will be a positive. Maybe negative 3. And if you need to actually write down the plugging in stuff, you're welcome to do that. I'm just trying to speed things up and just talk through things, but you're welcome to actually show the plugging in. I think this should be negative if you plug in something over there. Finish the analysis. Do the increasing, decreasing with the justification. Get the coordinates of the relative extrema. On your quiz on this stuff, which is not for a while, and on the test on this stuff, which is also not for a while, all of these will be asking you to justify things, so make sure we're using that appropriate language. Maybe something kind of looking like this for the analysis.
You think it? the majority of people were, left-handed, then like the left side of the graph would be positive, right side would be negative.
I don't know. I don't know. I'm not sure how to answer that.
Maybe. If the majority. Probably.
It would be good to show where they're coming from. Yeah, Ryan?
So there's even, what if the two extrema are different?
So, yes. Maybe the graph would look like this or something like that. These are both relative minimums. I don't really care. I'm not trying to find the absolute lowest y. That would be yesterday. This still counts as a relative min. This still counts as a relative min. So yes, they would both be good. And I'm almost certain that's going to show up, if not in the homework, then on like the review or something. Perfectly reasonable. Other questions here? I do want to show you one last function where we do increasing, decreasing before we get into our next idea. F of x equals x squared minus 3x minus 4 over x minus 2. How about you just get the derivative, simplify, and stop? Because there's something a little weird that's going to happen with the critical values. By the way, product rule or quotient rule? Don't move it up and do product rule. Just leave it as quotient rule because there isn't any chain rule that I see that would have to happen here. I hope we're finding a derivative. There's a lot of just sitting there going on in the front. Yeah, go do your derivative. Yeah, and do the derivative. Getting f prime is x squared minus 4x plus 10 over x minus 2 squared. There's an easy critical value. What are we getting from the bottom? Can you factor the top? No. If we can't factor, could this top still equal 0? What will we have to really use? Oh, that'll be fun. Here we go. This is, by the way, this is non-calculator, so that program is not going to help you. 4 plus or minus square root of 16 minus 4 times 1 times 10 all over 2a over 2 times 1. That is 16 minus 40. That is negative 24. So what? I don't care because they're complex, so we're not getting any critical values from there. The top is never going to change sign. I have only one critical value. Quickly go test and finish this one off. I'd use like 3 and 1 or 3 and 0 or something. Go test things. The regions. Not my patience. Shh. You know what? The bottom doesn't even matter because no matter what you plug in, what's the bottom always going to be? Positive, so we can really just plug into the top. You have your signs? They're both positive.
Uh-oh.
This means I'm increasing. Now, am I going to be allowed to say from negative infinity to infinity?
No.
What's wrong with that?
That's everything.
Well, right. Isn't that positive everywhere?
Yeah.
Except where? except at x equals 2. The first derivative is not positive there, so I'm not going to include that. I'm going to say I'm increasing from negative infinity to 2, and then 2 to infinity, because f prime is positive there. We should not include 2 because f prime is not positive at x equals 2. F prime is actually undefined at x equals 2. Maxes, mins, anything else? That's the best we can do. This graph is always increasing, except at x equals except at x equals positive 2. So something, hold on. Yes. Okay, so something kind of like this, where I'm increasing everywhere. There's actually an asymptote at x equals, we're going to say that's x equals 2. And then something like that. It's increasing everywhere. Just not at 2. Okay, so now we need to look at more information we can figure out about the shape of these graphs. And this idea is called concavity and points of inflection. This is going to move us into section 3.4. And you will see in a moment why we are doing this today. It is very closely related to what we just did. Concavity and these things called points of inflection. And you're going to make sure there's an L in that word. Inflection. Don't write that. But it has not. So, we already talked about increasing, decreasing, concave up, increasing, decreasing, relative max, relative mins. There are some more features we can talk about. We say that our graph is concave up anywhere it takes on the shape of an upright parabola. And we say that it is concave down anywhere it takes on the shape of an upside-down parabola. So I feel like this graph that I'm looking at that is increasing, then decreasing, then increasing, that has nothing to do with what I'm about to talk about. I think until that point that I drew over there, it takes on a concave down shape. I think that after that point, it's taking on a concave up shape, looking more like an upright parabola. Forget about the increasing, decreasing stuff. That's a different matter. And that point where it changes from one shape to another, we call the point of inflection. So I'm going to label that as a point of inflection.
That's where the bullet goes in. Oh, is that where it changes from like negative, was it something about 1, -1, or +1?
I'm not sure what you're talking
Or
about.
as soon as the like derivative stops.
Hold on for a moment to that. Let me give you the actual definition of concave up versus concave down. Because no, the actual definition does not say it looks like an upright parabola or looks like an upside down parabola. We've got to do better than that. This graph over here. Starting concave how? Up or down?
Up or down.
Down, and then concave up, changing about there. What I'm going to do is I'm going to put in a couple little tangent lines. Little tangent lines here. Maybe like this, and this, and this, and this, and that. Draw in some tangent lines. Little slopes.
Looks like it changes the side.
Yeah, but that's actually not going to be our definition, but that has something to do with it.
Wait, can I make a guess?
What's your guess?
Alright, so if it's going from concave up to concave down, that means that the slope stops increasing, okay, so if it's going like this, it's going from down to up, that means it stops, so if it's going positive, negative, it stops decreasing and starts increasing.
So what is actually saying is F double prime?
That's kind of where we're going. Watch carefully. I've got a positive slope over here. As I trace this thing out, less positive, less positive. What's happening to your slope?
It's decreasing.
The slope itself is decreasing, and decreasing, and decreasing, and decreasing, and then I get over to here. Now I'm in my concave up shape. What's happening to the slope as I move on?
It's increasing.
The slope is increasing. Concavity is really all about what's happening to f prime itself. My actual definition says f is concave up if f prime is increasing, which is not what we're actually going to use to test things. I'm going to show you that in a moment. F is concave down if F prime is decreasing. That's the actual definition of concavity, which is good, but maybe not as useful as we actually need it to be. Here's what we're actually going to use. F is concave up when so here's the deal. If anything is increasing, what's true about its derivative? Its derivative is positive. I told you that we're concave up where F prime is increasing. If F prime is increasing, what must be true about F prime's derivative? Positive. And what is the derivative of F prime?
F double prime.
F double prime. We are concave up where F double prime is positive. Similarly, F is concave down when? Well, if F prime is decreasing, that means its derivative is negative, and the derivative of F prime is F double prime, so where F double prime is negative. Concave up, going to look like one of those things. Concave down, going to look like one of those. One more definition, then I'll show you two examples. Points of inflection. These occur when we change concavity, when we change from concave up to concave down or down to up. There is no difference as far as we're concerned between the two cases. We don't have to distinguish between like the relative maxes and relative mins. First of all, these occur if F double prime of C equals 0 or if F double prime of C is undefined. And then I'm going to say that F has a point of inflection at x equals C if F double prime changes sign there. F has a point of inflection at x equals C if F double prime changes sign there. F has a point of inflection at x equals C if the second derivative, F double prime, is changing sign. So, let me show you how we can use this. First example. We are going to determine the concavity and points of inflection of f of x equals x to the fourth minus 4x cubed. And when we do this, we're going to justify everything that we do. We're going to determine the concavity and the points of inflection for f of x equals x to the fourth minus 4x cubed. We're going to justify things. I am not going to go and write out the step-by-step process for this because it is basically identical to maxes, mins, increasing, decreasing. I'm just not going to use f prime. What am I using?
Double prime.
Go find f double prime. And once you have f double prime, I think you need to factor that and find these aren't critical values. Critical values come from when the first derivative is 0. This is the second derivative. There is no like standard name for these. I usually call these places possible points of inflection because they could end up being points of inflection. So in this case, I'm going to say there are possible, I do not feel like writing up point of inflection. I'm going to say POIs at x equals 0 and 2. F double prime could change sign there. Don't know if it will, but it could. and make it a number line. How should I label it?
Double prime.
F double prime. Again, it's going to be important that we label these properly, since by the end of the chapter we'll be dealing with multiple number lines at a time. You need to test your regions. This is no different than before. We're just plugging into our second derivative. So plug like 3 into that, plug 1 into there, plug -1 into there, see what happens. While you're doing this, I'm going to get the homework out, but don't put it away yet, and the cumulative review as well. Test the regions, test in the second derivative. George, I'm going to give you one extra one to go back to Rob. You're a little bit closer. Yeah. A little bit. Jeez. One area of the room, I guess. Rob, I could have had you move up today. Next time they're all out, you can move up. Don't put the homework away yet, though, because we've got to do certain specific things on here. And I hope we're testing the regions. Let's get that done. Cumulative reviews, we're back to trying an AP pre-response question. This week is based on implicit derivatives, because I figured now we know how to do those.
I'm guessing this is not wrong, right?
No.
Homework?
No.
This,
That is not.
this looks like 3 nights.
Yeah, it's too nice. Because the last 2 pages are just answers.
Oh.
Yeah. Because every answer requires you to justify things, so they're a little late.
So it really just stops at 24. Yeah, okay.
Yes.
That's not bad.
Okay, so the signs. After 2, plug in 3, what do you get?
Positive.
Should be positive. Between 0 and 2. Before 0. As for my symbols, I am not going to do one of those. What do you think I should do instead? It's not increasing there. Yeah, those little parabola shapes. Concave up, concave down, concave up. I am concave up between -infinity and 0, and then between 2 and infinity. Why?
Because these are positive.
Don't say it. What is positive?
F double prime.
Thank you. Especially because F prime, we've got all those things I need to move up, sorry. We've got all those things we need to be very specific in our language, because F double prime is positive there. Concave down between 0 and 2, because F double prime is negative. Points of inflection. 0 comma something, 2 comma something, 2 comma something, because F double prime changes sign. How do I get the y values? Plug into the derivative?
Plug into the original function.
The original, F double prime, F prime.
Original.
Original always tells you y coordinates. My testing for my number line, that was absolutely happening with F double prime, because I wanted to know where F double prime is positive versus where it's negative. No, but y coordinates. First of all, do you see y, 0, and 2 are points of inflection? F double prime was changing sign there. I need to plug into the original, though, to get my y coordinates. So 0 minus 0, that's 0. Let's see, 16 minus 32, negative 16. I think I don't have time for another example, but I do want to, hold on, don't pack up yet. I'm going to stop this.